Okay, so let me also welcome everyone to my talk. It's a pleasure to be here and have the opportunity to present some of my work. So as was already mentioned, I will talk about factorization problems and the dimension dependence. So it's about factorization of operators on a certain class of Banach spaces called H-system Hardy spaces. And the talk is based on this paper of mine. So first of all, let me explain the setting and in particular define the class of spaces in which my results hold. Okay, so first of all, some notation. So the dyadic intervals are denoted by this D. So it's 0, 1, 0, 1 half, 1 half 1, 0, 1 fourth, and so on. Then if I is a dyadic interval, then I will denote the left half of I by I plus and its right half by I minus. And associated with a dyadic interval, we define the half function hi to be plus 1 on its left half and minus 1 on its right half. So it looks like this. And this is the interval I. Okay, so the first class of spaces, I will do this step by step, is called H-system space X. This is just the completion of the linear span of the H-system, well, together with the constant function to express functions that don't have mean value 0, but this will not be essential, under a norm with two properties. First of all, we demand that if x and y are finite linear combinations of the H-system and their absolute values have the same distribution, then the two functions should have the same norm. And the second condition is just some normalization, so the constant function should have norm 1. Okay, so this class was introduced by Lechner, Mutakis, Müller, and Schlumprecht, and it contains, for example, all the Lebesgue spaces for p less than infinity, and more generally, all separable rearrangement invariant function spaces on the unit interval, for example, Orlich spaces. Okay, for all these Banach spaces, the main results will be true, but we can also go one step further and define H-system Hardy spaces. So a H-system Hardy space is again the completion of the span of the H-system under some norm. Either we take this rearrangement invariant norm from the previous slide, or we take an associated square function norm, where the norm of some linear combination of the H-system is obtained by first taking the square function of this element and then applying the x norm. For example, if x is L1, then this would be the H1 norm. So you get the dyadic Hardy space H1. And from now on, by the letter y, I will denote some fixed H-system Hardy space. So, for example, an Ri space or one of these associated square function versions. Okay, now let's go to the problem that we're interested in. First of all, if n is a natural number, then by yn I will denote the linear span of the first n plus 1 levels of the H-system in our space y. So it's n plus 1 levels because we start counting at 0. And now we ask the following question. So for our given natural number n and some parameter delta greater than 0, how large does another natural number, capital N, have to be chosen such that the following holds? For every linear operator T on the space Y capital N, so on the larger space, with norm at most 1, and with delta large positive diagonal with respect to the H-system. So this means that if you view T as a matrix, so you take its matrix representation with respect to the basis, then the diagonal entries should be positive and at least delta. For every such t, there should be a factorization of the identity on the smaller space, y little n, through the operator t on the larger space. And in addition, we demand that these two involved operators a and b, which form our factorization, should satisfy some uniform upper bound. So they shouldn't be too large. In that case, 1 plus epsilon over delta would be the best thing we can hope for. So that's called the factorization constant. So the product of the norms shouldn't be too large. And we can also consider a variation of this problem where we don't assume anything on the diagonal of the operator t, but then we only get a weaker conclusion. We either get a factorization through t or through the identity minus t. For example, if t is 0, we cannot get a factorization through t. That's why we have two different cases. So before presenting my main results, let me give you some more context. First of all, consider the special case where we are working in the space capital LP for some p between 1 and infinity. There one can actually apply the restricted invertibility theorem by Bourgain and Zafrieri to obtain an extremely good result where the dimension dependence is linear, so the dimension of the larger space is linear in terms of the dimension of the smaller space. And moreover, there is some converse statement which states that if there exists a factorization through t, as described earlier, then the operator t is actually well invertible on a large subspace of its domain. So go back, to be precise, t will be invertible on the image of this operator b, and its norm isn't too large, so has a reasonable size. Another reason why these problems are relevant, and that's actually the version with two possible outcomes, t or identity minus t, that's Bourgain's localization method, which in some cases allows one to prove that a Banach space is primary by reducing this to such a finite dimensional factorization problem. Okay, some more examples. There are results in many different classical Banach spaces where this problem has been considered. For example, the bounded operators on little L2 by Blower, the dyadic Hardy space H1 and its dual BMO by Paul Müller from Linz, or L infinity of LP by Walk, and many others. So this list is far from being complete. However, the existing bounds for capital N in terms of little n are often extremely large. So there might be some tower of nested exponential functions of little n or something like that. This was true, for example, for the dyadic Hardy spaces until Richard Lechner in 2019, who, by the way, was my PhD advisor, proved that an inequality of the form capital N greater than a constant times little n is sufficient for the dyadic Hardy spaces HP and their counterpart SL infinity for p equals infinity. Okay, now let's go to the main results. Essentially, I was able to extend this result to an arbitrary H-system Hardy space. So let Y be a H-system Hardy space and epsilon greater than 0. Define eta to be some function of epsilon. And now I have this explicit lower bound for capital N. So if capital N is at least 42 n times n squared times something, then the conclusion holds. And now I first state the version with two possible outcomes. For every linear operator t on the larger space with norm at most 1, the identity on the smaller space factors through t or identity minus t with some reasonable constant. And in fact, if the the only thing that matters in this inequality is the dependence on n, so we might as well write it as n is at least a constant times little n squared. And if the Haar system is unconditional in the space under consideration, then in fact this inequality can be replaced by a linear inequality. So n is at least a constant times little n. And now if you look at the definition of the involved spaces, you see that the actual dimension of the space Yn is something like 2 to the n. So in the end, this results in a quasi-polynomial dimension dependence, and the linear inequality results in a polynomial dimension dependence. Okay, the same result with some minor modifications holds if we consider operators with large positive diagonal. So we introduced an additional parameter delta, which will appear somewhere in the constants. And then if we assume that T has delta large positive diagonal entries, then we get a factorization through T. And finally, one may ask whether this restriction to positive diagonal entries is really necessary. And if we omit the word positive, then one can still prove a result, but n has to be quite a bit larger, so something like 2 to the c times n squared. Since there is much more combinatorics involved, this increases the dimension dependence. But then, indeed, one can omit the word positive and just require that T has large diagonal entries in absolute value. Okay, in the remaining time, let me talk about the proof or the main ideas of the proof. So the basic idea is to perform a step-by-step reduction. We start with an operator T on the larger space, and we reduce it to some operators that are somehow simpler to work with. First, we diagonalize T to obtain a diagonal operator. This is called a Haar multiplier, D. And in the end, we want to obtain a constant multiple of the identity operator on the smaller space. That's our main goal, because once we have such a scalar operator, then it's easy to prove the desired results, because, for example, the identity clearly factors through c times identity or 1 minus c times the identity, because one of these two numbers is non-zero, so c or 1 minus c. Okay, so essentially c times the identity, that's our goal. And to perform these reduction steps, we construct operators A and B and some factorizations or approximate factorizations. And these operators are obtained by constructing what we call a faithful Haar system. I will explain in a minute what this looks like. And the operators A and B will always look like this. So essentially, we construct a new system and perform a kind of basis change to our system HI hat. And A reverses this basis change, essentially. Okay, so our system HI hat should, in some sense, have the same structure as the original Haar system. For example, the first function might look like this. Then it has a left successor and a right successor. The left successor should always cover the set where its predecessor attains the value +1. And the right successor should cover the set where its predecessor is -1. So that's the idea. And we have to choose these functions somehow in a clever way to obtain a factorization that gives us the desired results. So the first reduction step, the diagonalization step, works as follows. We construct a randomized faithful Haar system. So we choose some signs, theta k, where k is taken from the dyadic intervals, uniformly at random. And then our system looks like this. HI hat of theta is some finite linear combination of Haar functions hk with coefficients theta k, which are our random signs, ±1. We do this for a specific number of levels of the Haar system. And the important part in this proof, this step of the proof, is that the collection over which we take the sum also depends on theta, so it's also randomized. This is what's different from the work of Richard Lechner. In the unconditional case, this is not necessary, but in the general case, this more complicated construction is needed. I think it's best explained by some pictures. Now I will only focus on the first function, its left successor and its left successor. First function might look like this, and this is for the case where all signs are equal to +1. Then again, we have the same structure as described before. And now if we change one of these signs, let's say in the last level, then this just flips the function. On the other hand, if we change one of the signs in an earlier level, then this also moves around everything that comes below it. So this changes the support of the successor function. If we change this sign, then the half function on the last level will move around. If we change a sign in the first level, then everything below it will be moved to the right. Now we can go through all possible combinations, all possible choices of signs to obtain this randomized system. And now the question is, why is that useful? And the answer is we can consider the following random variables, xij of theta, which are obtained by taking hi hat of theta and applying it as a functional to t of hj of theta. So hj hat of theta, so we just consider the operator with respect to our system hi hat. That's essentially what happens here. And one can show, and this takes a few pages of computations, it's a bit tedious, but one can show that the off-diagonal entries, xij for I not equal to j, have expected value 0. And in any case, the variance of xij is very small. So it's at most something involving 2 to the minus m/2, where m is the first level that we use in our construction, so where we started our construction. So this means that by choosing m sufficiently large, we can use probabilistic arguments and Chebyshev's inequality to prove that for some realization of our random signs theta, the resulting system will almost diagonalize the operator t, because the off-diagonal entries will be close to their expected value. Okay, and this essentially completes the first step. And in the end, let me briefly mention the second step, which is a stabilization of Haar multipliers. So from the above arguments, we obtain a diagonal operator, a Haar multiplier, with some entries di. So hi is mapped to di times hi. And in addition, that's another benefit of this more complicated randomization technique, is that this Haar multiplier is already stable along every level of the Haar system, of the dyadic intervals. So this means that if I and j have the same length, intervals I and j have the same size, then di is approximately equal to dj up to some small error. So we essentially just have one specific number, one multiplier entry per level. Now we can use the pigeonhole principle to stabilize the Haar multiplier across all levels. So essentially to choose some specific levels where these entries are close together. And then using some perturbation arguments, this gives us the desired conclusion. This yields a scalar multiple of the identity, and then we're done. Okay, so that's all I wanted to tell you. I hope I could give you some interesting insights.